Hello and welcome to a video in which I would like to discuss with you multi-disc rotors and continuum rotors with an imbalance. So a multi-disc rotor is simply a rotor composed of one flexible shaft, and instead of one disc we will have multiple discs. Each disc has an origin, or is described by an origin, that is related to the theoretical connection between the two bearings. There is one point W, index I for the ith disc, which connects the shaft to that disc. And there is, of course, here a little bit exaggerated, a center of gravity. It will usually not be there, but in between these 2 points, that is displaced with respect to the connection point between shaft and disc. The discs are assumed to be rigid as before, and as I said again, the shaft is flexible and is described by its bending line by a bending beam. Now you can see again the coordinates here that matter for point Wi. The tasks we have is we want to describe, here it's shown in the y direction, but for the z direction it would be the same. We would like to describe the time dependence of the y and z bending displacements of now each of the discs by an equation of motion. And in order to derive the equation of motion, we basically have to do two tasks. The first one, we need a kinematic relationship for each disc between point W and point S, because we have to apply the inertia forces of each disc at point S, the center of gravity, while the restoring forces will act with respect to point W. And second, of course, we have to write down the equation of motion, which will then be composed by an inertia term and a restoring force term. And I will discuss the derivation now in the following. So let's start with the kinematic relationships. They are quite simple. They are just a generalization of what you have seen before for a Jeffcott rotor with a single disc to the case of multiple disc. So on the left-hand side, you will find the center of gravity of the ith disc. So it's just an index I that you have to add to the subscript S here. Same holds on the right-hand side. You will find the coordinates of point W. And then you have the distance E between the 2 points and the corresponding contribution in cosine and sine direction, which is co-rotating with omega, the rotational speed of the rotor. And as now there are several discs, you could perhaps set for the first disc the phi I to 0, but you cannot have this for any disc here. You don't want to change the orientation of the space-fixed coordinate system for each of the discs, but you will use one space-fixed coordinate system for the whole system. So therefore you have to introduce here that phase shift phi sub I for each disc. So basically E sub I and phi sub I have to be known beforehand. The coordinates, either the coordinates for the connection points, W sub I, all the coordinates for all the center of gravities will be governed by the equations of motion. And this leads me to the second part of the derivation. The first part, quite simple. The second part is now related to the deformation. I will for the moment just consider the inertial forces and of course the elastic restoring forces. Now the question is, how can I generalize the study of the classical Jeffcott rotor with a single disc to the multi-disc situation? Well, if you remember the stiffness, the bending stiffness that we used for the classical Jeffcott rotor, then this bending stiffness is obtained by considering single load cases. Namely, you apply a unit force at the position where you have the disc. A unit force in lateral or in vertical direction. The same could be done here. We apply a unit force that would be then exerted at the position of one disk, and we compute the response at the position of all the other disks. And finally, this would be one load case, and due to the fact that we are considering a linear elasticity, so we know that our problem is described by linear equations, we can use the superposition principle. So the total displacement at one disk will be influenced by all the other forces, which are then not the unit forces, but the concrete or realistic forces at the position of all the other disks. This is called the concept of the influence coefficients. So you have to determine the influence coefficients by studying single load cases, and then you superpose these single load cases to study the influence. These are the influence coefficients here of each force on the displacement. You can see that these influence coefficients, they represent kind of flexibility, so a kind of inverse of the stiffness, because they do not appear as coefficients in front as factors of the displacements, so they appear in front of the forces here. So this would be, I would say, the major task. It looks quite simple, but it's the major task of the analysis. Namely, it's a static strength analysis of a bending beam in order to determine all these influence coefficients. For certain cases, of course, you can find them in tables and classical textbooks on bending beams. But for more special cases, you have to derive them either by a computer program. Well, I would recommend that, or by hand. So what are then these forces here? Well, these forces, as the restoring influence is now represented by the influence coefficients, so inverse of the stiffness, is then represented by the only forces that will act here. These are the inertia forces. So we will not consider any damping here. So the inertia forces, in the sense of D'Alembert, have negative sign, so opposed to the y and the z direction, and they are composed by the product of the appropriate mass and the acceleration. So if you are still in the mood of the last video, then forget for the moment now about any angular momentum. Nothing is included here that leads to an inclination, so we do not consider inclination of the disks here. We go back to the simple case of the classical Jeffcott rotor, and therefore this contribution from the linear momentum theorem is sufficient here. Okay, now with that information, we can assemble our equation of motions. This is done on the next slide, which is to a large extent a summary of what you have seen before. The kinematic relationship plus the deformation described by influence coefficient plus the plug-in of the inertia forces, and at the very end you will end with an expression that includes here the inertia forces for the coordinates y, si, and so on, for y sub 1 and y until y sub n. So these are the contributions from the inertia forces. And then on the left-hand side, you see we have a tiny little problem. That's the only situation where you would have y sub wi and z sub wi. And due to the fact that we shift all these terms to the left-hand side of that equation, the inertia forces appear with a positive sign. And instead now, as having this mixed set of coordinates, y sub s for the inertia terms and y sub w in the deformation part, we now replace y sub w and z sub w by y sub s and z sub s. Why? because they are in minority, I would say. There are so many terms related to the center of gravity that for each equation you just have to change one term. So therefore we, in this case, exceptionally, so at the very end of the series of videos, we prefer to work in the coordinates with respect to the center of gravity here. So this being said, we have ys and zs here. All the other terms are shifted to the left-hand side, so they appear here. And then we have minus ey cosine omega t plus phi I on the left-hand side. We move everything to the right-hand side. So we move the e sub I cosine omega t plus phi I to the right-hand side with a positive sign then. And we do the same for the sine term. So these are the equations of motion. Again, well, for the homogeneous setting, or for the homogeneous system, we use an exponential setting. This leads to an eigenvalue problem. From the eigenvalue problem, you would find, first of all, the natural frequencies of the system, but with respect to the particular solution, of course, you then see that these natural frequencies correspond to the critical speeds, in the sense to a resonance phenomenon that should be avoided. And guess how many eigenvalues are there? So we have n equation, 2n equation in total, n equation in lateral direction for all these 1 to n disks. We have one equation of motion in lateral direction, one equation of motion in vertical direction. If all these coefficients are the same, so the masses are the same and the stiffness properties are the same in the lateral and vertical directions, so that the influence coefficients are the same, you just need to determine one n influence coefficients, then you would have n critical rotational velocities. When it comes to additional effects, so for example to a non-circular shaft where you would have these critical regions between several of these critical speeds, then the results are analogous. So if you have, for example, to a certain flexibility related to a non-circular shaft, you would have two of these critical speeds. Instead of having one for the classical Jeffcott rotor, you would have 2n here for the case of a non-circular shaft, and you would have that region in between that should be avoided. So you would have n regions in between that are bounded by these two bounds, which are these 2n critical speeds here. So everything is really analogous, goes analogously to what you have seen for a single disc rotor, and therefore it was so important to study the single disc rotor, and now it's easy to grasp or to generalize the results to the multi-disc rotor. So that's already done, quickly, right? Done. Now we move to the continuum model. So how about the continuum model? For the continuum model, I don't like that approach, I have to say very much, but it's really a simple approach. We cut out one element of that shaft. So for the continuum model, there is no disc. There is just a shaft that bends. But that shaft now has to carry the mass properties, so described by mass density here. There is no single disc anymore to which we apply the inertia properties, but the inertia properties are now smeared over the whole beam, and this is described by a mass density. So we cut out a small element of that beam and we formulate the balance of course, all the forces, the inertia and the restoring forces, or reaction forces here, in order to derive the equations of motion, which are now partial differential equations. So task one would be derivation of these equations of motion in terms of partial differential equations. Second task would be to determine the kinematic relationships. So what can be said? If you look at that element here, then that element has a certain length dx. the reaction force on the left and on the right end point opposite, but they are not the same because of that finite length delta x here. On the left hand side, they are denoted by qx and qy, qz and qy, sorry, and by qy plus delta qy, so they are allowed to change, and qz plus delta qz. And there are the inertial forces that point in opposite direction to the two directions that are of interest for us. That is the z direction, so delta tz would be the inertial force of this tiny little part of the shaft, and delta ty is the inertial contribution in or opposite to the y direction. And we do not consider the x direction here. This is the direction of rotation. We assume, as always, a stationary state here. So in total, we have the balance between the deltas, delta of the inertial force and the delta of the restoring or reaction force, because the contribution of qy and qz, so the non-delta term, cancel. Now we have to put some physics in these delta t and delta q, in these inertial contributions and reaction contributions. So for the inertial part, delta t here for delta ty, we write it as the product of mu, which is the linear mass density, so the product of the mass density rho times the cross-section area A, and we have to multiply the cross-section area A with delta x in order to get the mass of that part here. Yeah? Delta x in longitudinal direction, A the cross-section, yeah? So, or the area of the cross-section. So, and we have to multiply this by the acceleration. We simplify this expression. We take here the acceleration for that element with respect to the center of gravity. So in the same way as the theorem of the center of gravity tells us. We do the same with the inertial force in vertical direction. It's the product of the mass, which is written here as the linear mass density, rho times area of the cross-section, multiplied by delta x. So you get the mass of the tiny little element, and you apply the inertial force for the acceleration of the center of gravity here in direction w. So, and the sign is taken into account here by, well, in the sense of D'Alembert, by letting these forces point opposite. Now let's move to these shear forces, so these reaction forces in y and z direction. So the difference of the shear forces can be computed by taking the derivative. It's the derivative with respect to x, the partial derivative, which will be denoted by that notation comma x, qy comma x, delta x. The partial derivative of that shear force is equal to the second partial derivative of the bending moment. And for the bending moment, we can introduce the bending line, which is then minus E times I, Young's modulus, multiplied with the second moment of area of the displacement here in lateral direction. So we take it related to the geometric center, and we take here the second derivative of the bending line, multiplied by delta x. Same reasoning for delta qz. So now we have terms at hand for the inertia part, so for delta t. We have terms at hand for the shear forces, physical terms at hand, so we can put them all together, but we will need kinematic relationships, because the inertial terms refer to the center of gravity, qy and q sub z refer to some geometric center of the cross-section area. So the kinematic relationships have to be extended now in a continuous way, because at each x you can have a different kinematic relationship. So both sets of coordinates still depend on time, but they also depend on the position x. And this is the true generalization of what you have seen before, the multi-disc rotor, where you had a discrete version, and now this is a continuous version. You do not have an index here, but you have a continuous dependence on x here. So you have displacement fields, space dependent. The same now holds for these differences between S and W. They become now dependent on x. They could vary, depending on the local mass distribution, for example. And you also have to introduce here a phase shift and angle phi, and also that phase shift angle phi becomes now a field quantity or quantity that is space dependent. Now let's put all this together. So into these equations of motion. So on the one hand, we have the difference in the shear forces, which include the space derivatives here. And on the other hand, we have the inertia terms. And if we replace Vs by that expression for V sub W, we see that we obtain the same as before, namely we have to take the second derivative of the coordinates with respect to W, and the second derivative of these cosine functions, because they are time dependent. And again, as we study only the stationary operation, we neglect terms in omega dot. So we get the same analogous forcing function on the right hand side than we had before. We have seen before for the classical Jeffcott rotor, and it represents the imbalance, and it's now represented by mu times delta x times Ex omega squared cosine omega t plus phi x. We divide the whole equation by delta x in order to avoid that delta x here, and then the equations of motion are there. We have the contribution from the restoring force, so from the bending beam theory. We have the contribution from dynamics, and on the right hand side we have the forcing by the imbalance. And you can see it's a partial differential equation containing time derivative and derivatives with respect to our space coordinate. In order to be able to solve these equations, we need boundary conditions. These boundary conditions refer to, for example, if the bearings are at the ends, to the positions where you have the bearings. Let's assume they are at x equals 0 and at x equals L, and classical bearings, so they are immovable. So you really support your rotor by saying that the bending line has to vanish there, and they should be moment-free. So the second derivative with respect to space will also vanish there. In order to solve these equations of motion, you would also need initial conditions here, initial conditions for the set of displacements, so for V and W, at each location x for one time, for example, t equals 0 or t equals t naught or whatsoever. Here again, we will ask the question, well, what is the influence when it comes to critical speeds? We could do the same analysis as before, but it's much more involved because we are dealing here with partial differential equations. And I said I don't want to deal with partial differential equations here. That's the only excursion to partial differential equations in that course of machine dynamics. This is really the subject of machine dynamics 2 of the following course. So let me just give some analogy to conclude here. For the results that you obtain for a classical Jeffcott rotor, for the multi-disc rotor, and then for a continuum rotor. So first of all, if we look at the classical situation, you would encounter unnatural frequencies for the rotor with a disc. This leads resonance to n-critical rotational speeds. For a shaft as a continuum, you can show that you have countably many natural frequencies, so you also have countably many critical speeds. That sounds a lot, but countable is like integer numbers. They are countable. They are countable infinitely many natural numbers, but in between two natural numbers, there's a lot of space. between 1 and 2, there's 1.5, there's 1.7, 1.8, and so on. So you have countably many natural frequencies, countably infinitely many natural frequencies. You have countably infinitely many critical speeds, but don't be afraid, there's much space for you in between these critical speeds to operate, so safely operate your rotor. No problem. And of course, a very, very high critical speeds, they do not matter. You cannot approach infinity with your rotor, believe me. Yeah? Okay, how about additional effects? So, for example, if we have a non-circular shaft, then we have, for a rotor with n disks, 2n critical rotational velocities with an unstable intermediate region in between. We've discussed this for the multi-disk rotor. So for a shaft as a continuum, think again at these natural numbers. So you would have at each natural number, countably infinitely many, of these wedges that occur. So if there's a difference due to the non-circularity in the stiffnesses with respect to the body fixed coordinates, you would have 2 times countably infinitely many critical rotational velocities, and in between there would be these unstable intermediate regions. So this wedge, if you think of natural numbers, or if you transform your results to natural numbers, so that the natural frequencies correspond to one natural number, each natural frequency to one natural number, then there would emerge from each of these natural numbers, there would emerge such a wedge. And you have to avoid these regions. So the region in between 2 natural numbers, so the operational region is shrinked a little bit by this, but not so much that's not possible, that it becomes impossible to operate your rotor safely. So once again, the message is stay away from these critical regions and from these critical speeds, but there is a lot of space in between where you can safely operate your rotor. So that's all I would like to tell you about the Jeffcott rotor. I admit it's a long chapter. It's really the longest chapter here in the study of the bending bending vibrations of a rotor. I hope you learned a lot about not only the bending vibrations, this practical case, but also about the mathematics behind these bending vibrations, and that you saw that these tiny linear ordinary differential equations are much more complex, or include much more complex physics than it looks like if you study the single degree of freedom oscillator in engineering mechanics, and yet we are able to interpret and to use that physics in our real applications for the important case of rotor dynamics, of bending vibrations of rotors. This is the end of this very large chapter on bending vibrations, and I thank you very much for your attention. And in the next chapter, I will also study rotor dynamic systems, but I will go back to a rigid rotor, and I would like to study the balancing of rigid rotors. I'm happy if you join me in the next chapter. Thank you very much once again for your attention. Until now.